Alright, so welcome back. We're finishing up section 2.7 with the shifting or the transformation rules. So in our previous video we talked about the first two rules, which is the multiplier in front of x, whatever's multiplied in front of x, affects the curvature, or how steep the slope is. The larger the number, the steeper the slope, or the more narrow the graph looks. If it's a fraction between 0 and 1, it's going to look wider. It's going to go up slowly, be it shrinks the graph vertically, as the way the book would state that. Then the second rule was the negative sign, how that the negative sign will flip the graph either left, right, or up, down, depending on if it's on the x only or on the whole function. So that's where we're at. So we're to the third rule, which is the vertical translation. There are 4 rules, by the way. So the third rule is vertical translations. So we know vertically, moving the graph up and down. So when a number, a constant, is added or subtracted individually, you will move the graph vertically that many places. And you do it exactly how many places it says. You do not change the sign, which will sometimes come up in our next rule. But on this rule, you do what it says. So look at my examples with me. I have y equals x plus 3. This has the parent function y equals x, the simple line graph that goes through the origin normally. But this is an independent added 3. So it's going to scoot the graph up, translate it up 3 places vertically. So what would have been here is now moved up 3 places. So the graph looks like that. Then another example, we have our x squared graph, our parabola, with a plus 1. So that translates it up 1 place. So normally our parabola was at 0, but we move it up a place. Looks like that. Okay, the third example, we have our square root function, the little arc shape, and this time I did a minus 1, so the arc will be down a place from what it would have been. And then lastly, I have our rational function, or no I don't, I have our cube root function. You know, it has that shape like an S, and then it's moved down 2 places. So normally all of these kind of rotate around the origin. That's its original place. They all went through 0, 0. So I'm translating it from the origin and then down 2 places and then draw your shape. And plotting a couple points will be just great to kind of verify anything that you think there. But that is the rule. All right, the fourth rule, and then we'll put all of these together, is the horizontal translation. So the last thing that we need to know about 2.7 transformation is the horizontal one. So the horizontal translation, sort of like vertical, only it's when a number is added or subtracted dependently. So that's why I made a point about the independent, dependent. That's a little thing that comes up in this section. So dependently, when I use that term, I mean that it's included with the action of the x. It's in a parenthesis with it. It's specified to be specifically on the x variable, not on the whole function. So on the action of the x, so in a parenthesis, in an absolute value sign, under the radical with it, in the denominator, somehow specifically associated with the x value and that operation, that's a horizontal translation. And the thing is, you do the opposite. So it's a little extra thing to remember. You will translate it opposite direction horizontally. So the horizontal translation is always opposite from the sign. So for example, so if we had y equals, let's do our line x plus 2 like that. I guess that's not a good example because the line's going to be a special case, but we could use it on that, but it's not my best first example. So let me use the parabola. Let's do x plus 2 squared. So our parabola shape, the 2 is added to the x in a parenthesis to tell you that is a horizontal translation, not the vertical where the 2 is just independently outside of the parenthesis. So this is a horizontal translation. We'll move minus 2. On the horizontal axis, the x-axis, we move the graph back 2 places. So like that. Let's do the absolute value function. So this is our absolute value V shape because the minus 1 is inside the action of the x, inside the absolute value sign operation. We'll do the opposite. So it'll be positive 1. So moving it over 1, then draw your V shape. One more. Let's do the radical x minus 3. Y'all see that? Yeah, x minus 3 inside the radical, so that's not the outside independent one, is the vertical one. This is a horizontal translation, so we do the opposite. So we'll move our, what would have been at 0, 0, we move it over 3 places, draw the graph. And you might remember this makes sense because if you were making a t-table, positive 3 is the first number you can plug in for x that you're allowed to. Anything less than 3, you would have a negative under the radical, which would be imaginary, so it would not be part of our domain. So the domain, like we remember from our earlier lesson, starts at 3. So that's another kind of help you remember why it's the opposite. You can't put anything less than 3. It's got to be moved over to positive 3 to overcome that negative sign in there. So it's opposite. Horizontal translations are always opposite. All right, let's put a few of these together now, because what will happen is in your homework and work, you'll see they'll have all 4 of these rules thrown together to give you one big problem at times. So let's say we have y equals x plus 1 squared minus 2. So this is our parabola shape. The parent function is x squared. I don't know if you can still see that in that, but that is embedded in it, is the x squared parabola shape. This is a horizontal translation, so back 1 and then down 2. So take your basic parabola, it will be shifted from normally 0, 0, you go back 1, down 2, and that's where your parabola goes from. That's going to be its new vertex, is what we're going to call that. Okay, a second example. Let's put a negative sign in this one, radical plus 1. So this is our square root function. It looks like the little arc shape. It's going to be flipped upside down. You know, the negative is independent outside of the operation symbol, and independent negative, so flips it upside down across the x-axis and then moved up 1 place. Let's see, can I do that? So it's going to be this way and then up 1. So something like that. And then when in doubt, you're going to plot a point. Like if I just said, hey, that seemed a little outside my imagining, plot a point. Make sure you're in the right place. If you plug in 0 for this, the square root of 0, and then a negative sign doesn't change that. It's still 0. 0 plus 1 is 1. I should be at 0, 1, should be 1 point on my graph, and I can see it is. And then you could plot other points and verify that. All right. Let's do a couple more. Let's say y equals cube root of x. Let's put something under the radical with it for a horizontal translation. Let's put a negative in front of it and then a minus 3 on the end. So it's got a little bit of, a lot of things there. So the cube root parent function shape, we remember sort of looks like an S, and then it's flipped upside down. It's going to be back 1, that's horizontal translation, from 0, back 1, and then vertical translation is the sign that you see. So back 1, down 3, that's its new kind of turning point, pivotal point. And then normally, you know, it goes this way. Think of flipping that upside down, it's going to be like that. And again, plot some points. That's always a great idea. Okay, I'm forgetting to do the multipliers. Let's do that. So let's say we have y equals 1/2. Let's put a negative in front of that. X plus 3 squared minus 1. So I will see the embedded shape is the x squared parabola shape. I will need to flip it upside down because there's a negative in front of all of it. Notice it's not a negative inside the parentheses or in the action. The fraction makes it a little wider graph. It affects the slope. And then back 3, down 1. All right, let's see if I can do that. Back 3, down 1, that's its pivot point or its vertex in this case. It's upside down and make it a little wider. How much wider? You'd have to plot a point. But it is somewhat wider. If you had a multiple choice thing, you'd look at one that looks a little wider than the basic shape. But if there's 2, you'll have to plot a point. So you can't just absolutely know exactly what to do there until you actually verified some points on there. But that's a sketch. That's basically what it looks like. All right, to be continued.